Hello and welcome to the knockoff version of Crash Course. Have you ever been throwing a bowling ball at someone and then pillow to test the oomph and wonder what the impulse momentum theory is and all its specifics? Well, wonder no more. Because today in the knockoff version of Crash Course, we're going to be talking about the impulse momentum theorem and introducing our very own prototype to send a rover to Mars because planet Earth is dying.
In the arms of the angel, fly.
And our population doesn't believe in global warming. Anyway, let's get started. Leila?
Thanks, Michael. The impulse momentum theorem. When an object has a mass and a velocity, it has momentum. Since mass is measured in kilograms and velocity is measured in meters per second, momentum is measured kilogram meters per second. Time is one of the only things that can change impact on an object. A longer impact time means a smaller impact force, and the same goes for the other way around. In this lab, we're figuring out if this hypothesis is correct.
This whole test lab on our prototype was about buying time. By attaching a parachute to our lander, we significantly decreased the impact time from the moment the object was dropped to the moment it hit the ground. It made a soft and successful landing both times with different forces. We are confident in our build because we are sure that it will make the impact time much longer. The impulse momentum theorem is valid because without the parachute there to increase the impact time, the package inside would have been destroyed and the mission would have failed in a real world situation. Nobody wants a dead astronaut landing on Mars. Leila?
You right. Well, impact force and impact time go hand in hand. They run oppositely against each other. A longer impact time means a smaller impact force, and a shorter impact time means a stronger impact force. It's like dropping a ball attached to a parachute next to a ball without one. The parachute is there to increase the time and ensure a soft landing, while the other ball has nothing to decrease the time and will experience a stronger impact force. In two impulse momentum problems, if p is a higher number, chances are that t will be shorter than a problem where p is smaller. Here's an example.
An object with a constant change of momentum has an impact time of 0.5 seconds. What is its force? How about with an impact time of 2 seconds? Okay, so we know the change of time is 0.5 seconds. And we know the delta p is constant. So let's just say it's, to make it easy, let's say it's 2. And we know that delta p equals delta t times force. So let's just plug this in. 2 equals 0.5 times f. Simple algebra, divide by 0.5, divide by 0.5. What do you get? You get f equals 4. Okay, now with 2 seconds. Let's change that into 2 seconds. So we know delta p equals delta t times f. So now let's plug this in. 2 equals 2 times f, simple algebra, and you get that f equals 1. Now that shows that f is dependent upon delta t. If there's more delta t, that means f is smaller. If there's less delta t, that means f is bigger. Wait. What about the relationship between Vf, Vi, impact time, and force? Good question, handsome young man in the green jacket. Well, the relationship between Vf, Vi, impact time, and force is the same thing. They are directly proportional. The more impact time and force you hit an object with, the faster it's going to go. Here's an example.
A baseball is at rest. It is hit with a forward force of 10 newtons for 2 seconds. Its mass is 5 kilograms. I know, a heavy baseball. What is its final velocity? What about with a force of 5 newtons in 1 second?
Thanks, Leila. So we know that Pi equals 0. Why? Well, because Vi equals 0. And Pi equals m times Vi. So we plug those in, 5 times 0, that equals 0. Pi equals 0. We know that delta t equals 2 seconds, f equals 10 newtons, and the mass is 5 kilograms, like I said before. So we know Pi equals 5 times 0. So therefore, Pi equals 0. And now, delta p. In order to find out delta p, we have to do delta t times f. And we know what delta t and f is right up here because it gives it to us. So we know delta p equals 2 times 10. Therefore, delta p equals 20. Moving on to the next one. Delta p equals pf minus pi. Well, we know what pi is and we know what delta p is. So therefore, 20 equals pf minus 0. So therefore, because of this, pf equals 20. If you just do the simple algebra there. Moving on to the next one. Pf equals m times vf. Now we don't know vf because that's what we're looking for, but we know mass and we know pf. Pf equals 20, and the mass is 5. And from there, simple algebra, divide by 5 on both sides, and you get that VF equals 4.
Thanks, Michael. Now we're going to repeat that exact same process with our new information. Now we know that time is 1 second and force is 5 newtons. So we're going to repeat the whole process again. So in order to find PI, we need to know mass and VI, both of which we already know. So we're going to go ahead and plug that in. We know that mass is 5 kilograms and VI is 0. Therefore, making PI is 0. Now we're going to do it again over here. So we know time and we know force, but we don't know delta P. So we're going to plug those in. And now we know that delta P is 5. Therefore, PF equals 5. Now, down here at the last one, we know that PF is 5, and we know that mass is 5. So we just do simple algebra and divide by 5 on both sides, and we know that VF equals 1. Now originally, our method of decreasing the impact time on our lander prototype 1 was to surround the lander with springs and just have multiple small impacts hitting the object at once. We then realized that our method would put our prototype at risk of damage, so we decided to use a parachute on prototype 2 so that the lander would only experience one small impact force. We also protected the package from the inside using a cushioning device on both prototypes to protect it from impact. But wait, how'd you fix it? Great question, you Moana-looking teenager person.
See the line where the sky meets the sea. It calls me, and no one knows.
Our next prototype will still involve the parachute and inner cushion on the inside of the lander. There will most likely be an outside cushion on the lander as well. It will most likely be airbags. We are also going to make it a sphere shape instead of a cylinder.
2 and 1.
I am the one, the way your son don't need a gun to get respect up on the street under the sun.
Thanks, Leila and Moana-looking teenager. Thanks for watching our knockoff version of Crash Course. We hope that now you have a better understanding of the impulse momentum theory and our future plans for a rover, and will consider it for funding. See you next time.